All right, moving into our next modeling component, which is local modeling. So I'm not going to spend much time on this first page, but I'm going to do a quick review of global interpolation, what you just covered in the previous one. So what do I mean by linear, bilinear, and bicubic interpolation in terms of global interpolation? And then I'm also going to introduce local interpolation in terms of nearest neighbor, linear interpolation. We'll talk a little bit about bilinear interpolation, something called IDW, and again, briefly discuss cubic convolution. And then there's an entire video on Cricking, which the Cricking I am really going to touch lightly on because it is a statistical surface. So, but it is part of local interpolation. So we'll kind of bring it up a little bit, chat about it, but it is a little bit more complex than the rest of these ones. So a first order polynomial is known as a linear interpolation. So that's the a0 plus a1x plus a2y. A second order is bilinear interpolation. This is where we would have a0 plus a1x plus a2y plus a3x squared plus a4xy plus a5y squared. So that would be bilinear. And then a third order is bicubic, which I'm not going to go through all those. So the when I use those terms, that's what I'm referring to, and that's in terms of global interpolation. So you are going to see a linear interpolation in terms of local interpolation. So you're really going to have to really watch terminology, right? Global modeling versus local modeling are really important to watch. So global, any kind of variation is considered kind of random noise that we're trying to minimize. That's the idea of global. Local says, hey, you know what, maybe those local variations are important, and so we're only going to look at data within a single area. So we can either use a area, which would be known as our regular patchwise data, or we're going to have irregular, which is looking at number of points, which is the neighborhood. So I'm going to find the data points within the neighborhood or the search area, and then you choose a math model to represent the variation, and then you evaluate a height at an interpolated point. So that's really the big difference between them. So local interpolation, we have all these points in our data set, and I'm trying to find the height of that one particular location. So what do? I can do regular patchwise, which I say, here's the radius. I'm going to search everything within that radius, and then I am going to find my number of points. Or I could just say, hey, you know what? I just want to go by 4 points that are surrounding it, and then I'll go calculate it that way. So if my radius was maybe a bit larger, I might have this point that's included, and so there would have been 5 points in there. If my radius was smaller, I might only have 3 points. So the radius can dictate how many points because we're trying to keep it very local, like I'm very closed in, or we're trying to do number of points, which just helps evenly distribute the data around it. So some of the considerations is the size of the area, the shape of the region we're looking at. So I showed you a circle, but we can also change it to like an oval. We can change it to rectangles. We can change it to all kinds of stuff. And then also the orientation. Orientation is really important because, for example, if we're going along here in Calgary, and let's say I wanted to do I'm just trying to think of, let's say that there is a slope like by Sate, and if I had a oblong shape like an oval, and that was my neighborhood shape, and the size of it was a particular size, and there, like, if you know the slope by like the Jubilee, it's relatively flat, but there are some areas which it kind of curves in. So if my search area included that curve on the like on the far side of that circle, let's say, or the oblong shape, then it's going to actually impact everything within like that search area. Where if I went north-south, I'm not going to end up with that XY direction that's changing. as much. So you have to be aware of like how the slopes are formed in order to improve the accuracies of the of your local model. Also, the number of points is really important. If you are doing radius, what do you do if there's no points in the area? Then it becomes then it's not possible to calculate. We also have distribution of points, so irregular grid, whether it's tins, because tins also have their own form of interpolation on them. So if you have gridded data points, then we're going to change the kind of local interpolation versus like irregular. We also have the interpolation functions. So what are we really trying to calculate? How are we calculating it? Is there a better way? Is it more efficient? Is there a more accurate way, depending on the data set? Then we can incorporate trends and domains. So again, kind of knowing the general trend of the entire area is helpful. That's why global models are really powerful, because they can help identify what you need to do with the local interpolation. And then it also smooths the data. So there is a type of averaging that does happen with local interpolation, so you have to keep that in mind. So like I said, we're going to look at these 5 types of local interpolation. We have nearest neighbor, linear interpolation, bilinear interpolation, cubic convolution, and inverse distance weighting. Mathematically, you will need to know how to do nearest neighbor, linear interpolation, and IDW. The other 2, if you know what they are, then that's great. So we're going to do everything with grid data. So we're not going to deal with the irregular data. Again, really it's just to improve simplicity for ourselves. And then what we would do, like to do this math in real life, is if we took irregular data and then we created grids like rasters, and then we would actually calculate from the raster to do these. So this is done all the time. So yes, it may not be perfectly gridded originally, but we will grid it ourselves, and then we will rasterize, and then we can do these calculations. So jumping into the first one here, nearest neighbor. So nearest neighbor is exactly as it sounds. So what we're trying to do is find out a height of a point that we don't know based on the point that's closest. So you put your point in within your grid, or even irregular is fine. If it's not a regular grid, this one works the same way. And we calculate the distance of that point, and this is horizontal distance only, right? Because you don't have the height. So it makes it really hard to do 3-dimensional distance. So x and y. So you have x and y of this unknown point. You have x and y of 1, 2, 3, 4. And then you determine which one is closer. So then you take the d1. So for example, distance, this is 0.1 is showing to be the closest to the point. Then I assign the elevation value of 1 to the point. Do not assign the distance to the point. That is not the purpose of this. The x and y is totally different from the z. So, this is, and that's a common error that I see people do. So don't do that. So the z value is the z at the minimum distance of that from that point, right? So the z value of 1 is now equal to the z value of p. So keep it the same. So advantages and disadvantages. Well, we don't change any data, right? So it does stay the same. The value is always the same. You're not going to be interpolating in between. So you're not manipulating the data to create lines in between. But as you can see, it's very discontinuous. So we don't get a very nice and pretty diagram. It looks very much like, I don't know, I guess Minecraft or the original Nintendo games of Super Mario Brothers. Looks very cut off. And that's okay, because sometimes we're not looking for a beautiful model. In fact, if you are creating a highway, this is probably a better option, because if it's all curvy and stuff, the mathematics to calculate how to like cut and fill is going to be a lot more complicated than taking a flat plane that you can like put a road through here, right? So just something to keep in mind for that. So that's nearest neighbor. It's really fast, easy. Again, you take the elevation of the closest point and assign it to that point that you don't know. This one's a little bit more complicated. So we're going to take our gridded data and we are going to divide it into two triangles. And so we have 3 points that define a plane, which kind of looks like a tin, except it's gridded, so therefore it is. You can use it. You can definitely use this on a tin, I guess, if you wanted to, because it works about the same. But this one produces a smooth, or sorry, a continuous but not smooth surface. So you can see that there's some edges that you see that are developed from this type of interpolation. And again, it's okay. It's just the nature of what it is. so it's just that visualization that you know what to expect when it comes along. So how does this work? We have a square grid, and you have to number them exactly this way. Okay, so 1 is always in the origin, 2 is along the y, 3 is the one that's kind of out in free space, and 4 is along the x. And the reason that is so important is because of the math. So we have xp, which is the unknown point, which is right here. And then we minus x1, so we have to know wherever the first point is. And then we divide by delta x, which is the full distance between 1 and 4. So delta x. And then we do the same thing with y. Then we have to determine where is the point within that square. Is it in the top triangle or is it in the bottom triangle? So if the x bar is less than y bar, we know that it is in the top triangle. So 1, 2, 3. If it is the opposite, so if x bar is greater than y bar, then it's in the bottom one. So 1, 3, 4. So this is how we assign to this delta. So we have 1 or 0. So why is that? Well, taking this example, here is my equation. So in this equation, we can see that we have delta, and then we have 1 minus delta. So if delta is 1, it's going to be 1 times these values, plus 1 minus 1 times those values. So I don't have to worry about this last half of the equation at all. If it's 0, this front part becomes 0, and then I only need to worry about this back part. So that's all it's doing, is it's trying to identify between, is it in the top triangle or is it in the bottom triangle? And that's where this linear, and then we just apply these values. So we have the z values, and then x bar, which is what I calculated on the previous slide here. And then there's y bar, which is also on this page as well. So this really only works for gridded data. Linear interpolation is really picky about that. So let's just do, this one I'll just do a quick example here, just so you can see. So this is our global trend, right? That's where it comes from. So we're using 0.1. And this is deriving the equation, so using 0.2, we add in that. And then we add 0.3, which gives us a1 equals z3 minus z2. This is all deriving, right? Good fun of deriving. And so I'm giving you the formula here, so you don't have to derive, all right? But so this is where the formula comes out. And so we end up with z1 plus z3 minus z2 x bar plus z2 minus z1 y bar. And that's located in here. So if you want, if you're having fun, you can derive the lower triangle formula if that's something that you really want to do. There's no requirement for you to do that or to hand it in or do any of that stuff, but just kind of letting you know that you can have fun doing that too, or you can just use the one that I gave you. So again, that's kind of what it looks like in the end, is with these lines. You'll see some of the odd changes of surface normals. So bilinear, this one, you will not have to do any math. And so you take a grid, use 4 nodes instead of the 3, and you create 4 equations with 4 unknowns, and you go to solve for the unknowns and determine the estimated heights. Sure, easy. It's basically global interpolation. The only difference is that you're only using 4 points. So you do end up with a continuous surface, but it's not a smooth surface when you're dealing with bilinear. So there's the math up here. This is the original equation looking at bilinear, as you guys recall from global modeling. The only thing is that they just don't show x squared and y squared in this formula. But we have our little saddle that's developed here. So here's really like how it gets derived. I know some of you guys will be really excited about this, so you're certainly welcome to work through it. I am not worried about you being able to do the math on this, but I want you to be able to see what is happening. So here's the final equation, finding out the z value of this point. You would use this entire thing here. And so you don't have to worry about figuring out what side of the triangle or what side of the grid it's on. It's going to be somewhere in the middle, and then we're going to use all 4 points in order to calculate that. So you can see that the x bar, y bar, and xy are all basically weights on these elevations. And so that's really what it comes down to, is it starts weighting how far away it is based on the x and y distances. So then cubic convolution comes in. Again, this becomes a lot of fun because you need to use 16 points. It uses a curve. It kind of takes it into the frequency domain, looking at it, and then it smooths it out. So the example I show at the end looks kind of funny because it kind of overkilled the numbers, but it can be a very practical way of handling really large data sets. So you can see that we have our point, it kind of weights it based on a curve, and same with in the y direction as well. And then we have like these z and then the coefficients, right? So we have to include all of this. It becomes a really, really big formula. So the benefits of using a cubic convolution is that it's smooth. It's a smooth surface. It does take into account a lot more that's going on around it. But one of the disadvantages is that the edges kind of explode. They have some weird things that happen to them. So you have to be really careful with that. You may end up cropping out those edges. Data is money, but you may find that that's more beneficial. And because you're using more points with it, then you can say that it's more accurate. But again, sometimes accuracy calculations are kind of biased in themselves, right? So it's a lot more computationally expensive as well to do cubic convolution, as I showed you. That's why I would not ask you guys to do it, unless it was just like doing it in the software. So IDW is the last one. So we talked a little bit about how bilinear interpolation weights the z values. That is really the same idea behind inverse distance weighting. So this time around, I'm going to use distances as or an inverse distance as my weight. So I find the height of the point by weighting the nearby data points, and I can determine how many data points I want to use according to their distance from the interpolation point. So this is the formula that you would use. Again, the mathematics is not that crazy difficult because it's really just taking sums and adding it up. It just looks like a lot once you start putting it all together. So you have your z value of your point, and again, remember we're doing local interpolation in this case, so we are looking at the observed value. You divide it by the distance that it is to the unknown point. Okay, so the unknown point, then this is the known point, and the distance to that point. Now P here does not stand for point. P stands for the inverse weighting. So I can make it a 1, I can make it a square, I can make it 3, I can make it 4, I can make it 5, I can make it 25. The higher this P value, the less impact anything at a distance is going to have on the actual calculation, right? So the further away you are, the less impact that this Z value will have on this calculation. So we do the Z over the distance, and we add them all up. And then on the denominator, we do 1 divided by the distance, making sure that the P is the same. And then you add it all up. Distance is the planimetric distance, so my Euclidean distance in 2 dimensions, x and y. So the known point minus the unknown point. I've had people in the past say, well, if you don't know the point, then how do you know the x and y? And it's like, well, how do you plan on figuring out what the elevation value is at a random point that you don't know where it is? So it's like, I'm standing here, I want to know what the elevation is here, which means you need to get the x and y value at some point throughout that. So yeah, so just to kind of remember that you will always have the x and y value in order to determine the elevation. So here's an example of the weighting. So you can see that like at 1, everything's way up here. So every value is going to be high. And then as we increase the distance, the amount of weight actually drops. So it means that there's less and less impact as we go. And then the same with d squared. You can see how much more it comes down. And then once you're at 6, you can see that it drops really rapidly the further away you go, to almost like a 0. Okay, so this is a bad picture that didn't show up very well. This is a power of 2. Again, this one's really meant to interpolate between unknown points. So it has some weird effects that happen if you're trying to show a visualization. So it's it doesn't visualize very well. And so that's something to keep in mind as well with local interpolation, is that they're really not meant for visualization purposes. They're meant for mathematical purposes. So the last one is Cricking. I do have a whole video on Cricking that I go through really fast. So the Cricking video is for FYI, basically. It's for your own information. It's not going to be tested on in this class. It's not going to be quizzed on. It's not going to need to come up. The only reason you would ever bring it up is in this class is really just because you used it. You do not need to do anything mathematically by hand with Cricking. It is a little bit more complex. So it is a very commonly used type of ground-based modeling, because it's statistical, so therefore it includes more information and provides a better evaluation of its accuracy than these other ones that we've just finished talking about. So Cricking and splines look very much the same. Splines are a little bit different, but so if you ever see the word spline, it has a relationship to Cricking, but they do look different in the end. So that's what Cricking looks like. It does pick up on like anomalies within the data sets, so it will represent those a little bit more accurately. So you can see that it becomes a continuous smooth surface with anomalies that are brought in from the data that it has had. So Cricking kind of ends up with like a little bit of a miracle. So if you want to see the miracle, please see my Cricking video, and it will be very quickly covered, but you'll get a chance to see that. So in summary, we looked at the nearest neighbor. We looked at nearest neighbor, linear interpolation, bilinear interpolation, cubic convolution, and IDW, and like briefly mentioned Cricking. So mathematically, you need to be able to do nearest neighbor, linear interpolation, and IDW. Bilinear interpolation and cubic convolution are just for your knowledge, that you know that they exist. So I will see you in some examples. I guess you will not see me, but see my examples in the local interpolation video for examples. So you'll get to see some math there.